yesterday we looked at the angular momentum principle, and so that combined with Newton's laws will give you the equations of motion for a rotating body. We will use that today to analyze this case of a person using their shoulder muscles to perform an exercise using dumbbells. Okay. So, let us say we have the arm is assumed to be weightless and of length L, m is the mass of the dumbbell. And we will assume that at the shoulder you have reaction forces So, if this is x y, this is j x and j y, and there is also a resistive moment. So, this is not a free motion. So, it is not like a pin joint about which this arm is going to be freely moving. There is some resistance, that is resistance moment, that is being provided by, let us say, an Fm. Okay. An abductor muscles of the shoulder, in this case most likely the deltoid muscles, and let us say it acts as an angle phi to the long axis of the arm. Okay. So, we will first, in some cases of rotational motion, it is actually simpler to use a coordinate system instead of the xy Cartesian coordinate system. We will use a coordinate system that is the r theta system. So, that is, let us say I have a coordinate system that is one aligned along the rod. So, let me call that unit vector E r, and I have E theta. So, one for rotational motion, it is convenient to have E r is your radial direction, and E theta is the unit vector. So, unit vector, the caps denote the unit vector along radial direction, and E theta is the unit vector along the tangential direction. And these can be related to, so basically my coordinate system I have, if this is I, this is j, okay, then this is E r, this is E theta, and this angle is theta. So, I can relate the unit vectors of the two coordinate systems. I can say E r, what would be E r? So, if I take, I can project it on the I j coordinate system. So, I can say E r equals yeah. So, this is sin theta. So, I have sin theta along the I direction, it does not matter how. So, here I am taking it in this. So, depending on where how I take theta, I can write sin theta I minus cos theta along j. Okay, this is the y component. So, this is cos theta, it is a unit vector. So, this is sin theta. So, ER is sin theta along I minus cos theta along j. E theta is, because these vectors will change with theta, ER and E theta will change. So, they are attached to the rotating body, and as the body rotates the coordinate system changes. So, E theta I can write it as, if this angle is theta, then this angle is also theta, the angle between E theta and I, this angle will also be theta. So, I have cos theta along I plus sin theta along j. Now, these are changing vectors in direction, right. Unit vectors, the magnitude remains the same, but the direction changes. So, I can find ER dot. Okay. ER dot is cos theta into theta dot, because I do this by d theta times theta dot along I. Differentiating this term, I get plus sin theta into theta dot j. Now, if you look at this, cos theta I plus sin theta j is nothing but E theta. So, DER, the rate of change of this vector is nothing but theta dot along E theta. Okay. Similarly, d E theta by dt equal to E theta dot. If I differentiate that, I get minus sin theta into theta dot along I plus cos theta into theta dot along j. This is nothing but minus theta dot into ER. Okay. So, we will use these when we try to find the velocities. So, I can write the position of this mass. Okay. So, R of, let us say this is P relative to O is nothing but L along ER. Okay. So, the velocity of this point P, which is d, I will omit the O because we are doing it with respect to, it is understood that it is with respect to this inertial frame. We are talking about the absolute velocity. So, this is, if I differentiate this, L dot does not change, there is no change in L, the mass is located at that. So, L remains L and I get dER by dt, which I know is theta dot E theta. Okay. So, L theta dot E theta. This is your omega r that you are familiar with in rotational motion. Okay. Now, let us look at formulating.
In this case,
yes,
the insertion angle, will it remain same throughout the whole?
That is an assumption we make. We assume that phi does not change. We assume the insertion angle of the muscle does not change in the course of the motion. So, now if I find the acceleration of P, I have to differentiate this again. So, I have L is constant first I differentiate theta dot, I get theta double dot along E theta. Then E theta is also varying. So, I get L theta dot E theta dot. Okay. So, this is L theta double dot along E theta, plus I know that E theta dot is minus theta dot E r. So, this becomes minus L theta dot square E r. Again familiar from circular motion, right. So, this is theta double dot is generally designated as alpha, your angular acceleration, and theta dot is your omega. Okay. So, theta dot is omega, angular velocity, and theta double dot alpha, angular acceleration. Okay. So, you can see that I can always express this now back in terms of sin theta and cos theta by going back to my I and j coordinates, because I know, but I will just keep it like this for now. Okay. So, now my equations of motion are, so sigma f, so let us say instead of jx and jy, okay, it is more meaningful for me because I am expressing in terms of ER and E theta. I will just call these reactions JR and J theta. Okay. I am taking two other orthogonal components for the joint reaction, JR and J theta. So, now I can write sigma Fr, my equations become sigma Fr equal to mass times the acceleration in the radial direction, sigma F theta equals mass times the acceleration in the tangential direction, and then sigma m naught, because O is a point that is fixed, I can write that as d h naught by dt, where h naught is the angular momentum about that point. So, let us compute the angular momentum. I have only one particle here, I am assuming the rod is weightless. Okay. So, my h naught is only r cross m v of p, r p cross m v p. Okay, I am using small m everywhere, so I will just change this to small. So, this is R p is L E r cross m, V p is L theta dot E theta. Okay. So, what does this give me? M L square theta dot along E r cross E theta is again just k, m L square theta dot k. Okay. You can also look at it as the moment of inertia of this mass about the point O, mass times that L square here. Okay. So, now if I do d h naught by dt, okay, I get d h naught by dt equals m and L square do not change with time. So, I get theta double dot k. This is your familiar I alpha, okay, I naught alpha. This is alpha. So, now I can write these three equations to solve for. So, I have to know theta, theta dot, theta double dot, or theta as a function of time. Okay. Knowing theta as a function of time, I can use these three equations to solve for the three unknowns, which are j r, j theta and f m. Okay. So, let me just write down those three equations. Sigma f r, this gives me, if I do that, sigma f r, first I can just solve for, if I take moments about O, I am eliminating two of the unknowns. So, it is easier for me to write this equation first, this equation. So, I will do that, I will do the sigma m naught, that equation, and I get f m sin phi times, I should know where the point of insertion is. Okay. So, let us say that is this distance, let us say is a, again known from anthropometric data. Okay. So, I have f m sin phi into a minus m g, okay, the component perpendicular, this is theta. So, this is m g cos theta and this component here is m g sin theta. So, and it is creating a clockwise moment. So, taking counterclockwise as positive, this becomes minus m g sin theta into L, okay, that is equal to m L square theta double dot. I can write this as a scalar equation because everything is in the k direction. The planar case. Then, so I can solve for f m from this relation, then using the summation of forces in the r direction, in the radial direction, I have j r plus m g cos theta minus f m cos phi is equal to m a r, which is minus m l theta dot square. And summing the forces in the tangential direction, I have j theta minus m g sin theta plus f m sin phi, and what is the acceleration in the tangential direction? M into L theta double dot. So, theta as a function of time, theta, theta dot, theta double dot can be measured in a lab setting. So, using that, because these are things that cannot be directly measured, your internal forces cannot be directly measured. So, you can use a model like this to estimate the internal forces based on external measurements of the kinematics and the known external forces, known forces. Okay. Now, if you consider the arm to have a mass m a, then what would you do? Here we assumed arm is weightless, arm has mass m a and is of length L. Then you would have, let us say it acts at the middle, you have another m a g. Okay. Now, what would you do? Let us say we assume the mass is concentrated here. Okay. Then what you would do is you would basically just find the center of mass of these two masses. What would be my, if I take RCOM, okay, along ER, right, that this would be m a plus m, this would be equal to m a into L by 2 E r plus m L E r. So, my RCOM would be m a L by 2 plus m L by m a plus m. So, I would just have to find the resultant center of mass, assuming these are point masses. Okay. We will come to a problem where instead of assuming it as point masses, we consider it a uniformly distributed mass. Okay. So, here it is, you will just lump these two, find the center of mass, lump these two masses there and perform the same analysis. So, instead of L you would have RCOM and the new mass of m a plus m in the previous equations. Because the velocity, everything you would compute for the center of mass. So, when you apply Newton's laws, here when you say sigma f x or sigma f equal to m a, the acceleration is for the center of mass of the system.
Inertia also you have to calculate.
Inertia you will have to calculate. Inertia you would have to calculate. Okay, but again if you are assuming that the sum of these two point masses. So, if you say arm has a mass m a concentrated at its center, okay, then your moment of inertia will be different from if you assume it is uniformly distributed, and we will do that the next. We will look at a case where the mass is uniformly distributed, because that you will take into account in your computing the angular momentum.
Even in this case, when you will be substituting with the point center of mass, then also you will have a moment which is about of these two masses about the center of mass, which you will have to add in that, right?
Yes.
So that also we will have to calculate in this case.
Yes, in this case you will have to calculate the center of mass. So, the center of mass will be the center of mass about the CG of this, these two, about the center of mass of these two bodies, plus the, you will use the parallel axis theorem to then compute it about O. You compute the I about the, so if this is say the center of mass, you will compute I about the center of mass, which will basically be, m a times this distance square, then m times this distance square, that will be your moment of inertia about the center of mass of the system. And then to compute the I about O, you will do this plus RCOM square into m plus m a. Okay, when you compute the center of mass about the. if you do the angular momentum formulation, it will kind of come into the, it will automatically come into the equation. This you need to do separately only when you are directly using sigma m naught equal to I naught alpha. Okay. If you use the angular momentum formulation and then differentiate that to get it, it will automatically come into the equation. Now, let us look at the case of angular motion. So, you have a gymnast. Okay. Here you want to really find out how the gymnast is going to move under the influence of gravity. So, the gymnast is holding on to the bar with the wrists. Okay. So, it is essentially there is no moment being supported. Okay. You are not resisting any moment, the pin joint cannot support, cannot resist a moment. So, they are essentially going to move down under the action of gravity, and we can try to find the equations of motion of this movement. Okay. In this case, let us say that you can represent the gymnast by a rod of uniformly distributed mass m, and let us say the length is 2L. Okay. Let us say so, if I look at the CG, so if this is O, I have the CG will be at L. So, let me draw the this would be mg, this is point O, I have the reactions at the pin joint, which is at the wrist, and then this distance is L, this distance is L. So, the wrist acts as a pin joint about which the gymnast rotates. And let us say the gymnast is let go from a horizontal position. So, somebody, you know, you have seen that in the Olympics, they will hold them in that position and then let them go. Let go from the horizontal position. They sometimes do this upside down. They have their feet into the rings and then they will have their arms outstretched and then move down like that. Okay. So, they can be modeled as a rod like this. So, if I look at this point C representing the center of mass, I can write. So, again I can choose a coordinate system ER, E theta, and I can write R of the center of mass is LER. The velocity of the center of mass is L theta dot E theta, okay, and the acceleration of the center of mass is L theta double dot E theta, the tangential component, minus L theta dot square E r, the centripetal component and the tangential component, or the radial component and the tangential component. So, let us formulate the equations. So, first let me try to compute the angular momentum in this case, where it is a uniformly distributed mass as opposed to a concentrated point mass that we had in the previous case. So, if I look at the angular momentum about O, for discrete particles we said it is sigma Ri cross m Vi. Okay. Now, this is a continuous rod of mass m. So, we will write this as an integral. We will say this is R cross V dm. Okay. So, I take a slice of mass dm, because the velocity in rotational motion, the velocity of every point is going to be different. So, for each dm the velocity is going to be different, it depends on its radial distance from the center of rotation. Okay. So, r cross v dm is my angular momentum about O. Okay. Now, how can I express this dm? The total mass of the rod of length 2L, has mass m. So, if I take a small mass dm, I can write this as m by 2L dl. Okay. So, this dm has a length dl or dr, sorry, I should write it as dr. This element has mass dm and is of length dr. Okay. Now, I can integrate this h naught equals integral 0 to 2L, okay, dr varies from 0 to 2L of m by 2L let me put it r cross v is, what is v? R theta dot E theta, right, and dm is m by 2L dr. So, r E r times E theta is just k. So, I can remove the, just call this r E r, okay. In vector form it is that, or in scalar form, because everything is along the k direction, I can write this as 0 to 2L. M by 2L is a constant, it comes outside, and I have r square theta dot dr. Theta dot is also a constant. For all the points on the rod, the angular velocity is the same. Okay. So, I can bring theta dot out as well, 0 to 2L r square dr. this would be r cube by 3, 0 to 2L. So, I get 4 by 3 ml square theta dot. That will be my angular momentum. The sum of the moments equals d h naught by dt. If I differentiate this, I get 4 by 3 ml square theta double dot. Okay. Now, let us see if whether this is your familiar I alpha. Okay. You have this rod of length 2L. Okay. Its moment of inertia of a uniformly distributed rod about its center of mass is 1 by 12 m into L square. In this case it is 2L length square. Okay. So, this gives me ml square by 3. Now, the moment of inertia about the point O by the parallel axis theorem equal to IC plus m times the distance here is L square. Okay. So, I have ml square by 3 plus ml square, which is 4 by 3 ml square, and theta double dot is my alpha. Okay. So, this shows that this is equal to I naught alpha. Okay. So, now I can find the reactions. Okay, I have, are you guys familiar with the kinetic diagram? Have you heard that term before? In a dynamics problem, if you have a rigid body, okay, acted on by multiple forces, okay, and let us say its center of mass is here, okay, and this is equivalent to this, the rigid body. You have mass times the acceleration of the center of mass and I alpha, IC alpha. This is called the kinetic diagram. The resultant of all these forces equals this. It is essentially using the Newton-Euler equation. So, you have sigma f equal to m a center of mass and sigma m about the center of mass equals I c alpha, where alpha is the angular acceleration. So, this is how you determine the linear and angular acceleration. So, using the, so instead of formulating angular momentum each time, you can always use this kinetic diagram. If you know the moment of inertia about the center of mass, then you can use that to find, you can use this diagram to set up your equations of motion. Okay. So, in this case here we have J r j theta, I have m g Those are the only forces acting on this. Okay. This is equal to, this is the center of mass, I have some acceleration and I c alpha. So, this okay, I should not draw this neatly perpendicular to it, I should draw it some random m a center of mass. M a center of mass equals both the radial and the tangential components. So, if you look at the previous slide, this is c, right. We found the acceleration. Can you tell me what we found the acceleration to be? We found acceleration of c as L theta double dot along E theta minus L theta dot square along E r, that is A c. And what did we find I c to be? M by 12 2L square. So, m by ml square by 3. Okay. Remember, we have taken L as 2L here, that is why usually you will see ml square by 3 for the moment of inertia about the fixed pivot.
In this case it will change.
Yeah, that will
If we are
change.
writing out C, then we will find that.
Yeah. So, now when you have the kinetic diagram, the reason it is helpful to draw the kinetic diagram is like this equations are applicable to the center of mass. Now, if I want to take moments about some other point A, okay, then I have to make sure that this, the moments about A equals the moments about A in the kinetic diagram. So, that way I will not miss out this MAC, taking the moment of that MAC force about this other point, because otherwise you will just, I will show you tomorrow in the next class why that is the same as doing the I naught alpha when A is a fixed point. Okay. We will stop here because we are out of time, but using the kinetic diagram will prevent you from making some of these common mistakes when solving dynamics problems. Okay. So, we will get to that in the next class.